Hi. Now what we are going to do, we said uh, for analyzing sequential circuit, we categorize the sequential circuit. We said Moore machine and Milli machine, and we said the analysis, uh, there are small changes between those two sequential circuits, so we will be now examining the Moore machine analysis. As you know, the analysis circuit is given to you and an input sequence is also given to you. We're going to find the output sequence. Uh, so what is given? The circuit is given. As you know, as you see here, circuit is given. Uh, and for any given input, figure out the output sequence I said. For this one, what we're going to do is this. We are going to find the model. You know, the model of a sequential circuit, there are three different models. One of them is the mathematical model, the other one is state table, and the third one is state diagram. Those three models could be used for analysis. So the first step I will do here is to find these models. So once we found these models, then for any given input, we can figure out the output sequence. So step by step for this example, we are going to do this. So let's examine this circuit now. This circuit is has got one input, isn't it? This X. So if I draw a box here, so this box is like that. There's one input and one output and three state variables. So let me write those. X, Z. The state variables are y1 and y2. So we know all the variables now. So for this one, we said we are going to find out the three models. One of them is mathematical model. The second one is state table. And the third one is the state diagram. So let's start from the mathematical model. Once we found the mathematical model, we can easily find out the state table and state diagram. So one more thing that I need here is the definition relation of T flip-flop. So let me draw the definition relation of this T flip-flop here. T is the input, 0, 1, and for each memory element there is one state variable which is y, so small y is 0, 1. When t equal to 0, no change. When t equal to 1, if the input is 1, then whichever state you are in, it's going to be the opposite next state, isn't it? 0 becomes 1, 1 becomes 0. That's toggling. So inside we've got capital Y here. So let's start with mathematical model I said. So since we've got one output here, that means in mathematical model I've got to figure out Z next output function, and then since we've got two state variables, I'm going to find out y1 and y2 next state functions. For Z function, I just look at the circuit. Z function, this is y1 and this is y2. It's coming from y2. So Z is equal to y1 times y2, isn't it? So if I write y1, y2. Just remind you one subject, all these mathematical model dependent functions depends on independent variables. What are the independent variables in this circuit is that small this x and small y1 and y2. I said small y1 and y2. And so never write here capital Y1 and Y2. If you write that, that means you are writing one dependent function in terms of dependent functions. You should write a function in terms of independent variables in this mathematical model. So I wrote this capital Y1 and Y2 and never do it, put that in. Don't do it, just remind you. So how we are going to figure out the capital Y1? First, we're going to write the definition Y1. Y1 is this, isn't it? The output of this first flip-flop. The output of first flip-flop, I need the definition relation of this. What is this definition relation? I can write it here. So that is y prime time t, y prime time t, and y time, small y time, t prime. So for this first memory element, I am going to write y1 prime t plus y1 itself t prime. So this function here is the definition relation. So that's the next state function for in the definition relation of the t type memory element. But this is not the function that I am looking for. Why is that? Because that t is not the independent variable. So I've got to transfer this t function to independent variables that I mentioned here. But this y1, I'm going to keep y1 here because this is an independent variable. So if you look at t, where is t? That's going to be t1, of course. So the indices must be the same for the next state, capital Y1 in this. So Y1 prime, put that in, I need that. For T1, look at the circuit. Circuit tells this is X time. Look, follow this up. This is Y2, isn't it? That's Y2. So T1 is X time Y2. So I write here X time Y2 plus Y1 time T1 prime. So T1 was X Y2 prime. So if I write it once again, this in the order of, let's change the order here. That's the first one. So this one is equal, if I use the De Morgan theorem, this is X time X prime time Y2 prime multiplied with Y1 X prime multiplied Y1. The second one is Y1 Y2 prime. What I have done is this. Instead of this, I put this and multiplied this summation with that Y1. So distribution theorem, distribution axiom that I used. So I found now Y1 here. What about Y2? Move it a bit down. Y2 is Y2 prime, definition relation, T2, Y2, T2 prime. So Y2 prime, I keep this. T2 is this, isn't it? So if you follow from here, it's just X. So that is X plus Y2. So T2 is so X prime, X prime. So this is the second one. So this is the mathematical model now. So if you give me an input sequence, I'm just writing an input sequence here. Let's say this is like this. Time is this, so this is going to be applied first. 1 0 1 0. What is the output? In order to say that that's the input sequence, let's say X. If your present state is 0, 0 at the beginning, because there are 4 states, which state you're going to apply this input? So you've got to give the initial state as well, initial state. What you're going to do, for example, here, if your initial state is 0, 0, so that means y1, y2 is equal 0, 0, and x is 1, x is 1. So you can find out z function, capital Y1 and capital Y2 prime, capital Y2 values by using this model. So that means you're going to find capital Y1 and capital Y2 from this equation. So that's your next state. For the second input in your sequence is going to be applied on this state, at this state, let's say. So you're going to follow it like that, find out all the others. I'm not going to do it step by step. I showed you how you do it, so you can finish it up. Because one of the reasons behind that is this state diagram is going to be the easiest. We are going to see that state diagram is going to be the easiest analysis tool for a simple circuit. So that's why I'm not going to continue on that. So once we've got this, this is mathematical model. Let me write it somewhere here. Mathematical model. Once you find the mathematical model, then you can draw the, let me draw it here, state table. State table it's going to be a 3-variable function. Why is that? Because we've got 3 independent variables, don't we? So let me use this, make it a bit better. Nice looking one. This is a 3-variable Carnot map. Because these are the functions that I'm going to transfer to that Carnot map. Once I transfer this Carnot map, it's going to be state table. Why I am using the Carnot map? You can use any other map. Why I'm using Carnot map? Because these functions are the Boolean functions. So once you know the Boolean function, it is easy to transfer this function to Carnot map rather than the other maps. So I'm going to put here the order of Carnot map. So y1, so let me make it y1, y2, 0, 0, 0, 1, 1, 1, 1, 0. This is Carnot map order. So x is equal to 0 and x is equal to 1. Now since this is a Moore machine, because of this, so that means z function does not depend on the input sequence. So I'm going to write z function separately here, and I can write this immediately as the output, isn't it? Because if you know the small y1 and y2, you can write the z. So z0, 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 multiplication of those two. So this is not, of course, 0, is it? Multiplication of those two gives you 1. So that's 1 and that's 0. So I transfer this z function now to my state table. So I will be transferring y1 and y2, capital Y1 and Y2 functions to here. How I'm going to do it? From this function, isn't it? So this is a Y1, this is a product term, and this term is 1, 0, 1 input. This becomes 1, isn't it? So x is 1, so that's column, and 0, 1 is that row. So I'm going to put 1 here for capital Y1 function. So transfer, so this is like that. You can consider this one. So this one here, x prime y1, that means one variable disappeared. This variable value should be 0 and 1. So this is the summation of two true minterms, isn't it? So in these true minterms, one variable is changing. This variable is y2, and value of this y2 is going to be 0, 1. So for the x0 means 0 input, and y is 1. For y2, it could be 0 and 1. So x0 column is this one. Y1 row is those two. If I put 1, 1 here, now I am saying this is a first order subcube. Y2 variable is going to disappear. It is true, yes. Here you are. The corresponding y2 is 1. Corresponding y2 is 0. So this is changing. So this is going to disappear. What is left here is y1. And this column is x prime y1. So let me do it in different colors. So this term here, corresponding ones are those two ones. This one is y1, y2 prime. That means x1 value is changing. So I'm going to put now 1, 0, isn't it? 1, 0 is this one. So this one and this one gives me that product term. Let me make it different color now. So this one and this one corresponds to this product term. So for the other cells, the value of y1 is going to be 0 because these are the 4 ones that includes that y1. In other cells, that's going to be 0. I put zeros for those. Okay. So I'm going to transfer y2 now. y2 is x y2 prime. x1 is this one. y2 prime is this 0 and this 0, isn't it? So I put 1, 1 here. So let's go backwards. Now if you consider those two ones, that makes a first order subcube. In this subcube, y2 value is changing. Y2 value is not changing, while y1 value is changing. So y1 disappears, y2 prime is going to come in for these two ones, while x is equal to 1, x is equal to 1. So this one. So let me different color, make a blue, yes. So this one and this one corresponds to this product term. And this one, x prime y2, x prime y2 is going to be this 1, 1. X prime y2 is not changing, and this is x1. So these two, make it a color, this 2, 1 here, the first order cube corresponds to this product term. Okay, so all the others are going to be 0. So what I have done here, transfer these next state functions to that kernel map and transfer this set output function here. So for this, let's say for this input sequence, how I am going to find out the output is easy. So you see, you're going to apply 0, 0 state. When you apply 1, your next state is this. The first thing that you're going to observe is this, and your output is this. Now, for the first clock pulse, this is your next state. So your next state is the same as present state. But for the next input, that's going to be your present state. That means here. And you're going to apply 0. You're going to apply 0. You're going to apply 0 here. So this one, isn't it? So you're going to come back to this now, and it's going to be 0. So this is a strange circuit because, I made a mistake. So your next state, I made a mistake. Let me to correct myself. I said your next state is 0, 0. No, your next state is 0, 1, not 0, 0. So for the present state 0, 0, you applied 1, that's the 1, and your next state is this. So you came to this state now. For this state, you're going to apply this 0. You're going to apply this 0. That means that 0. Your next state is going to be this now. Let's make it 2. So when you are in this state, your output is 0, and you came to this state 0, 1, so the same state again, isn't it? So you are in this state, and you're going to apply 1. You are in this state, you're going to apply 1, your next state is this, 1, 0. So that means that's 3, isn't it? So that is this state, so your output once again is 0. So that for the third clock pulse, this is your next state. For the fourth clock pulse, your next state here is going to be your present state, and you're applying 0, you're applying 0, your next state is this. So this is your fourth next state, and this is your fourth output, isn't it? It is not changing, so this is 4. 3 and 4 is this, isn't it? So that means for this input sequence, you're not going to observe Z output as 1. So it's going to be always 0. So let's do the last model. The last model, as says here, state diagram. How I'm going to state diagram? I'm going to find the state diagram from the state table. Easy. Since I've got the 2 state variables, that means I've got 4, in the state diagram I'm going to have 4 states. Let me clear this area a bit. This one. 4 states, 0, 0, 0. So 0, 0, 0, 1, 1, 0, 1, 1. You see, I wrote all this a bit upper side, this states. Why is that? But I'm going to write the Z function just underneath that states. Why is that? Because this is a Moore machine. Moore machine means Z output depends on small y's. So that means you can, without looking at the input, you can write the output once you know that small y's. So that's going to be multiplication of, as we see here, multiplication of those two gives you 0. That's the output Z. And that gives you 0, that gives you 0, and that gives you 1. Now let's complete the state diagram. If your present state is 0, 0, if you apply 0, your next state is 0, 0. So it's going to be like that, isn't it? If your present state is 0, if you apply 1, your next state is 0, 1. So that's going to be like that. If your present state is 0, apply 0, comes back to itself when it is 0, isn't it? If your present state is 0, 1, if you apply 1, your next state is 1, 0. Your next state is 1, 0. Present state 0, 1, next state 1, 0. When you input is 1. So the third row, maybe third row. So if you come, your present state 1, 1. If you apply 0, your next state is 1, 0, isn't it? So it's present. What I have done here, sorry. When your present state 1, 1, if you apply 0, your next state is 1, 1. So you're going to come back to itself when input is 0. If your present state is 1, 1, if you apply input 1, your next state is 0, 0. So present state 1, 1. You apply 1, your next state is 0, 0. So let's examine 1, 0 row now. 1, 0, if you apply 0, your state is not changing. It comes back to itself when input 0. When input 1, your next state is 1, 1. So I'm going to put 1, 0. If you apply it 1, your next state is 1, 1. That's the state diagram. You see here, I said in this state diagram, I can easily find out the output sequence. So for this one, for example, let me explain by using the red color. Your present state is 1, 1. Before you apply the clock pulse, you're going to observe that 0. So when you apply 1, your next state is going to be this. So you're going to see that 0. And if you apply 0 here, you're going to see that 0 once more. That's that 0. So if you apply 1, you're going to apply that 0. You're going to come back to that state. Your present state is this. You're going to come to this. That's the 4. And if you apply 0 here, that's 0. So you're going to see this once again. So as I said here, the output sequence for this one, it was 0, 0, 0, 0. So you see here 0, 0, 0, 0, 0, 0. So I wrote here after the clock pulse value as well. So I hadn't shown, so it was going to be like that. So we haven't observed any 1 here, but I can show you how we can observe it. So if I apply, let's say, if my present state, initial state, let's say, let me change the color. Now let me write it here. Initial state. Assume that this is 1, 0. So that means your initial state here. And if you apply 0, 1, 0, 1 here. So same sequence. So maybe the order is different. No, okay, so let me change it to exactly the same. So 1, 0, 1, 0. I'm going to apply in that present state. So that's the present state. If you apply the present state here, before the clock pulse, you're going to observe this 0. So if you apply input 1 here, your next state is 1, 1. So once you came to this state, immediately you're going to see this 1 at the output. So that's going to be after the first clock pulse. So we are in this 1, 1 state. If we apply 0, this 0, here, this 0, apply 0, you're going to apply this 0 when your present state is 1. Your next state is 1, 1. So you came back to here. So 1, 1, you're going to apply 1 this time. So when you apply this one, so let's make it double. So your present state 1, 1, your next state become 1, 1 again, showing that 2 green nodes here. And in that state, apply 1. So that's that 1. Your next state is this, isn't it? As soon as clock pulse comes, you're going to observe this output 0. That's 3. So in that state, if you apply 0, this is this 0, that's the third 0. That's the third state. Apply this, you come back to 0, 0 state, so that means you're going to see that 0 once again. But in here, when you come here, this, you applied 0, okay. So if I write here, you're going to see, so 0, 1, 0, 0, I'm going to observe. So that means in this sequence, I could see output 1 here. So I didn't see any output 1 for this case. You see, same input we applied, but the output is changed. Why is that? Because we changed the initial state. We start from this green one. For the first one, we start from this 0, 0. So that's 0, 0, isn't it? So initial state here is 1, 0, but in here it was 0, 0, that one. That's the difference. So normally, maybe there's one thing missing here. If you got an input sequence, your output sequence is going to be the same length. So that means 4 input sequence, 4 bits include input sequence, means you're going to see at the output 4 input output sequence. But one thing more is this. If your present state, before you apply the clock pulse, you've got a present state. At that present state, before you apply the clock pulse, you're going to see the output as well. So for the initial state, if you consider one output as well, the total number of bits that you're going to observe at the output sequence, the first one before the clock pulse, the others after each clock pulse. So in this case, we are going to apply 4 clock pulses, but at our output sequence is going to be one missing here. Maybe that's going to be 2, 3 here, and this is 4, 5. So that's the end of this video then. So we finished the Moore machine analysis.